So the last episode ended with a diagnosis. A Go service with a 2 CPU quota running on a 64 core node. 64 Ps fighting for 2 actual cores because the runtime never looked at the cgroup. Throttled by the kernel every 100 millisecond period, and I told you Go 1.25 fixes it. Which it does, but I also promised you the fractional CPU trap. What happens when your limit isn't even a whole number? Say 500 milli-CPU. Because the biggest surprise in this fix bites the team who did the right thing years ago. There's a one-line snippet, runtime.GOMAXPROCS of runtime.NumCPU. It's been sitting in main function for a decade. As a harmless make sure we use all the cores ritual. On Go 1.25 that exact line is an opt-out. It silently disables the new behavior and some frameworks and libraries run it for you. So today, the deep dive. What GOMAXPROCS actually controls, how the new cgroup-aware default computes its numbers, including for that half a CPU, and how to avoid quietly opting back into 2015. Let's define the thing properly. Number of CPUs Go uses is close but wrong in ways that matter. GOMAXPROCS sets the number of logical processors the scheduler maintains, Ps, the same capital P processors from last episode. And each P can run one Go routine on an OS thread at a time. So GOMAXPROCS is the ceiling on how many Go routines execute simultaneously, not how many exist. How many are on a CPU running code right now? That ceiling matters in 3 places. CPU bound parallelism, obviously more Ps means more work in flight. Scheduler overhead, less obviously every P carries its own cache, and more Ps means more coordination and lock contention. And the garbage collector, which sizes itself off GOMAXPROCS. During its concurrent phases, it targets roughly 25% of CPU utilization. That's dedicated workers, about a quarter of your Ps, plus ideal workers on any free P. And what GOMAXPROCS does not limit matters just as much. Go runtimes blocked in syscalls or IO don't count, and neither do threads created by CGO. So the GOMAXPROCS set to 2 with 1,000 Go routines parked in ePOL, totally fine. The threads actually running Go code are capped at 2. The waiting room can be as big as it wants. Now, the pre 1.25 default, the mechanism behind everything we watched last episode. If the GOMAXPROCS environment variable wasn't set, the runtime computed the minimum of 2 things. The host's logical CPU count and the CPU affinity mask. That's it. The cgroup CPU quota, the thing Kubernetes actually uses to enforce your limit, was invisible to the runtime. So a 2 CPU container on a 64 core node got GOMAXPROCS as 64. The damage came in 4 flavors. Cgroup throttling. 64 Ps burn a 2 CPU quota almost immediately. Then the kernel freezes every thread in the cgroup until the next period, and the tail latency explodes. GC amplification. At 64 Ps, that 25% target means 16 dedicated GC threads, plus idle workers. So a single GC cycle can blow through the quota even when your code is under budget. Scheduler overhead. 64P caches and 64P rings of coordination for parallelism the cgroup will never allow. And the nastiest one, mutex holder descheduling. The kernel pauses a thread that's holding a lock, and every waiter stalls until it comes back. The Uber published numbers on this in automaxprocs readme. A real service 2 CPU quota at the host default of 24 Ps, about 22,000 requests per second. P99.9 around 76 milliseconds. Matched to the quota at 2, almost 45,000 requests per second. P99.9 around 26. Double the throughput and third of the tail just by telling the runtime the truth. directional numbers. Your workload will differ, but the table is why automaxprocs became the standard equipment in the Kubernetes deployments. Here's what Go 1.25 actually does. The default is now the minimum of three things: host logical CPUs, the affinity mask, and new, the cgroup CPU quota divided by the period. Then one more rule on top: the result gets flowed at 2, unless the host or affinity mask genuinely has only one CPU. The fractional cases are where it gets interesting, because Kubernetes limits are so often fractions. Go 1.25 rounds them up. 500 milli CPU, the ceiling of 0.5 is 1. Then the floor of 2 kicks in and you get GOMAXPROCS 2. 1500 milli CPU also lands on 2 and 2500 gives you 3. And notice the distinction. Last episode's 2 CPU quota gets 2 straight from the quota. The half CPU pod gets 2 only because of the floor. Same numbers, different reasons. Now, if you have been running Uber's automaxprocs, and statistically you have, this is a different answer than you are used to. Because automaxprocs rounds down by default, unless you opt into roundup. Two different answers, both defensible, both slightly smug about being the obvious choice. Goes says you paid for that half CPU, so use it. Uber says stay under the quota and avoid the throttle. Neither is universally right. What matters is that they are different, and your fractional CPU service will notice during migration. And the floor of 2? That's the runtime refusing to auto-set GOMAXPROCS to 1. Go GC workers and your Go routines fighting over a single P visible pauses. Sub 1 CPU quota usually belongs to bursty workloads anyway, and a 2 Ps let the runtime itself burst. If you genuinely need one, a tiny latency sensitive service, set it explicitly and measure. How does the runtime actually find the quota? It reads its own cgroup membership from the proc file system /proc self cgroup plus the mount info to find the CPU controller. Then it reads the leaf cgroup's limit files. On cgroup v2, that's cpu.max. On v1, it's the quota and period files. Mixed setups work, and a v1 CPU controller takes precedence if one exists. Now the Kubernetes translation. This is where people get surprised. Your resources limits CPU become the cgroup quota. That's what feeds the GOMAXPROC. Your resources request CPU becomes CPU shares, CPU weight on cgroup v2. That's a relative priority, not a ceiling. So the runtime explicitly ignores it, which by the way means a pod with no CPU limit still defaults to host CPU count. No limit, no change. And here's the part I did not expect. It's not a one-shot decision at startup anymore. By default on 1.25, the runtime's background monitor keeps watching. It rescans the CPU count, the affinity mask, and the cgroup quota about once a second, less often when the process is idle, and it adjusts GOMAXPROCS live. Resize a pod in place with vertical scaling, pin or unpin CPUs, change the limit on a running container. The runtime follows along about a second later, no restarts. Which brings us to precedence, because this is where the migration trap lives. And the thing to internalize, it isn't a static ranking, it's temporal. The runtime honors the last explicit instruction it got. At startup, if GOMAXPROCS environment variable is set to a positive integer, that's your value, and automatic updates are off. Calling runtime.GOMAXPROCS with a positive number does the same. Your value updates off. And here's the subtle one. Calling it with a value it already has still counts. You changed nothing and still disabled the new behavior. But none of that is permanent because runtime.set default GOMAXPROCS new function wipes the slate. It recomputes the default from current host, affinity, and cgroup state. It ignores the environment variable and any earlier explicit call, and auto updates resume. Call runtime.GOMAXPROCS again after that, and the explicit value wins and the updates die again. Last writer wins every time. So look at the trap again. Runtime.GOMAXPROCS of runtime.NumCPU at the top of main for a decade. That was a no-op with good intention. On Go 1.25, it's an explicit override that reinstates the old broken behavior and kills live updates. And you set it explicitly. You genius. Worse, some web frameworks, test runners, and libraries make that call for you. So audit isn't just your main function, it's your dependency tree. One more layer, go debug. Setting container max procs to 0 makes the default computation ignore cgroup limits. Old Go 1.24 behavior that applies whenever the runtime computes a default, even inside said default Go max procs. Update max procs is a separate knob for the periodic rescans and the footnote that will bite someone you know. Those defaults follow the language version in go.mod, not the toolchain. Build with a 1.25 toolchain while the go.mod still says 1.25 and you get the old defaults. The fix you upgraded for silently absent. One honest complication before the takeaway. The roundup choice isn't free. A cgroup quota is an average over period, not a cap on instantaneous parallelism. A 2 CPU quota with a 100 millisecond period means 200 milliseconds of CPU per 100 milliseconds of wall clock. And you can span that two ways. 2 threads flat out the whole time or 4 threads flat out for half the period, ideal the rest. GOMAXPROCS caps the instantaneous side, so matching it to the quota's average reduces the kernel throttling and usually helps tail latency, but it sacrifices the ability to burst within a period, which means for a busty latency sensitive service, either defaults goes round up, Uber's round down might be wrong. And the only honest answer is to benchmark. Theory loses to a WRK2 run every time. So, the takeaway. Unusually clean for once. If you are on Go 1.25 or later in a container with a CPU limit set, stop touching GOMAXPROCS. Remove automaxprocs unless you specifically depend on its round down behavior, its logger, or its minimum option. Make sure go.mod actually says Go 1.25 and then go hunting. Every runtime.GOMAXPROCS of NumCPU call in your code and your dependencies is a regression now, not a best practice. That single line is the biggest remaining source of we upgraded and nothing changed. Go 1.25 replaces mostly works by accident with correct by default. A 500 milli CPU pod owning 64 Ps was never healthy, and the runtime is finally honest about the world it lives in. The full write-up is linked below: tables, file paths, debugging commands, and if you are following the series, you know where the subscribe button is. Next episode, we cross to the memory side, the garbage collector, container memory limits, and why Go mem limit is the centerpiece of not getting OOM killed.